to uh, devote the time for the academics when it comes to academics and research when it comes to the family time. So sometimes we need to compromise with things as this field is progressing very rapidly. So catching up is very much needed. So from quite some time, people are involved in this quantum minor and this QT modules. You might have gone through all the theory part till date. What we will be doing today, we will going to approach from the perspective of experiments or experimental realization. So basically, we will be looking for the devices which could be utilized in realizing qubits, especially. And once you realize the qubits, you can do lots of applications when it comes to quantum computing. Those applications we will be touching. It's a survey kind of thing. Wherever some background, the knowledge, the mathematics and the theory, the physics is required, so those things we will definitely discuss. Okay, right. So let me directly jump into the discussion right straight away. We planned, we will be doing first semiconductor devices. The later half of the session today means first 1 hour we will be doing semiconductor devices. The later hour, the next hour, we will be doing superconducting devices. So both will be useful when it comes to quantum technologies. Okay. So as anybody has any questions, like earlier, please put up your messages in the form of queries. We'll be discussing when and wherever possible. Okay. Right. Okay. So the topics when I had to see this survey of semiconductors, topics to be covered is what are these semiconductor quantum materials? Okay, especially these quantum materials in the sense we will be seeing things at a quantum level, tiny level. At that level, what happens? We'll be talking about spin and charges of electrons or few collection of electrons. Okay, so basically we'll be forming something like a bunch of electrons confined in a space which are called quantum dots. So what are the quantum dot devices which will be using for computing, quantum computing? And there is also we are going to touch something called defect based quantum systems. The systems are by nature perfect, are close to perfect. We are going to create imperfection in them, or existing imperfection can be used for some application. So that is what device based quantum systems at the quantum level, by the way. And when it comes to these things are seriously application prone or application offering equipments or means. Okay, so especially for a medical sensing and also at the same time for the communication also, these things are known for offering a very good applications. Okay, so let me go further to the next slide and see what we got here. Okay, like I mentioned, if I take a semiconductor materials, I can explore, create qubits. Once I have qubits, I'm going to be able to realize a large memory. Well, let's say n qubits I realized, I will be having 2 to the power of n memory. I can make those qubits interact. So in a way, information being processing together. So in this process, what we can do is we will be able to do a quantum bits processing with an exponential speed up, which is specifically needed for certain tasks. So basically some optimization kind of a task which we can do using these things, optimization process. Okay, next, what else we can do? Yes, we can do with the networks of qubits. We can extend the network. Let's say, as we know, The stationary qubits are spin qubits, like electrons being in spin, or electrons with some set of electrons having certain amount of charges. If I confine them to a certain three-dimensional or one-dimensional or two-dimensional space, they're going to exist in multiple charged quantum states. The moment multiple charged quantum states, if I realize, straight away I can say I can pick couple of charge states and create a bit out of it, a qubit out of it by inducing a superposition, a transition between these two states. Just like electron being moving back and forth in the ground and excited, in the same fashion, the charge states of a bunch of electrons can be fluctuate between certain amount of low charge, certain amount of high charge. Okay, right? Some state. So this is how I can realize charge-based qubits, make them connect, and when I have one charge-based qubit at different points, they have to talk or communicate to flying qubits like photons. So this is how I am going to create a quantum communication network or protocol. Okay. Basically, if I am able to do this, what I can achieve when it comes to applications is, as we know, the quantum qubits travel along the way in the form of quantum states. Let's say, let me take a board and let's say I have a node 1, node 2. This is node 1 and node 2. You can say them as stationary qubits. Okay, another stationary qubit. Now the information has to travel, that I do it through quantum channel. Basically, photons are traveling along this channel where photons are carrying the information in the form of their superposition. Basically, photons can be in a superposition of, say, their horizontal polarization and vertical polarizations superpositions. Okay, when it comes to stationary qubit, probably the quantum information would be alpha 0 plus beta 1, where the states can be ground state energy or the highest state energy, or low charge state or high charge state, something of that sort. I can have a communication. So here, these photons are seriously sensitive for the external disturbance. Okay, if there is any Eve, third party, Eve is there, his presence or her presence can easily be known by the two parties at node 1 and node 2. Okay, it can sustain secure communication by ensuring that Eve is present or not. Eve is present, they will completely disregard that channel and redo the same process of communication again with the photons. Okay, so this is quantum network for you, which I can do with the semiconductor materials and using a defects based devices, okay, which are happen to be a very good coherent material, means their superposition states can last for very long, and moreover this defect based quantum qubits are very good when it comes to work at room temperature, and moreover they are very sensitive to the external magnetic field and electric field, which means I can use them to measure ultra precise changes in the magnetic field around from location to the location. Okay, so this is a physical measurement quantity that we can do using quantum sensing. Okay, so if I pick a quantum materials realized, like a quantum devices realized out of semiconductor material, I can put them into three sections in the context of what applications they can offer us. One is communication, another one is computing, that is optimization, another one is medical application sensing. Okay, so each domain here requires a physical systems capable of maintaining a coherent quantum states. Means very good coherence time is very much needed. Okay, let me go for that. So semiconductor platforms for quantum devices. What devices we had, or somebody had actually explored till date. If you say they can offer, or what we can do, it is possible with the manipulation of electron spins, we can realize the semiconductor devices, or we can realize semiconductor platform for coming up with a semiconductor device, electron spins. Okay, and the next one is charge states. If we see nucleus is there, electron is there, the nucleus itself is revolves on its own magnetic on its own axis. It's constitute a small magnetic moment like north and south, small bar magnet. In that, the small nucleus is this electron is there. Probably it is like opposite spin. Okay, so there is a in the presence of external magnetic field of the nucleus, this electron that is going to experience a magnetic field due to the nucleus. In that magnetic field, it's probably going to show some kind of a changes. That changes we can probe and we can induce some kind of a effect. Realize, I'm sorry, we can realize a superposition state by doing some fiddling with such kind of a setup. Another one, like I said, charge states. We will see in detail what is this charge state of few electrons put together. Okay, and there is also one interesting thing is if I just take an atom, by nature its charges are electrons are in the ground state, means the lowest valence state. The supply energy, the electrons will go to the highest excitation state. They are going to create an excited atom. So it is called excitons. These excitons are like say readily available energy sources. So these energy sources is are readily able to give. If somebody come to them, they will immediately share that energy. They become de-excited, and the excitation energy required, whatever excitation energy taken, that is transferred to the donor. So that is what the excitons are known for. Okay, Lakshmaranji is asking here, can you please give a practical examples of where it is being used with the real world cases? Okay, yeah, especially quantum computing in the era of NISC. Definitely, we'll touch those things as we go through. Okay, right. So right now what we are trying to do, we started with why we need to go for semiconductor devices. What applications they can offer? Number one is computing, communication, and sensing. Among them, what kind of a hardware is involved in realizing per se qubits in the semiconductor material? That is what we are looking at right now. We are looking at electron spin, could be a electron spin inside a semiconductor material. I'm not talking about electron anywhere in the free space or somewhere inside some medium. It's not that. I'm talking about electron inside a semiconductor like gallium arsenide. Inside that, that spin is going to experience internal magnetic field and also the other nucleus around. From those nuclei, it is experiencing magnetic field. It is going to respond to that magnetic field. In that way, by making it to respond, we can put it to a superposition. Charge states means there is specific things like quantum dots are realized using that kind of a idea. And excitons, we'll see how excitons are involved, for example, in getting higher dimensional photons. And when it comes to defect states, there is something called nitrogen vacancy centers. This is also we'll going to touch. So four ways if I had to decide when it comes to hardware in semiconductor materials. One is single electron being confined into a space of semiconductor material, or bunch of electrons confined to a space, or semiconductor atoms being excited by giving an electron. Let's say it's like a donors, acceptors and donors, like a holes and charged ions are prepared, right? If I remove an electron from a atom neutral, it becomes a hole, means it becomes a positive quantity, and wherever the electron won't occupy, it becomes an ion. So in that way, excitons are prepared. When the excitations like excited atom ion goes interacts with a hole, what happens? The excitation energy is transferred to the positive hole. Basically, that is what the redistribution of energy between two entities. Okay, so here the key advantages in this four hardware cases is the scalability is very good. Okay, so what we can do, we can even connect the existing CMOS nano fabricated devices to these things, because these are charged based things. You see, so CMOS is complementary metal oxide, okay, semiconductor devices which are known for giving field effect transistors, FETs they call. So those FETs can be connected to this any of these four types of charge based or say exciton based or spin based device. Okay. And one more thing is IC compatibility. You say I have already a chip, electronic chip is there. I can integrate or connect that electron chip to my superconducting charge based qubits. Okay, integrability that is called. And basically it is integrating with the classical electrons on the chip. Means, see, please remember, always people talk about classical and quantum. Okay, somebody may ask a question. See, even in the classical computers, like a real world, regular existing computers, charges are flowing into the hard disk, or the flowing through the processing unit, and it's a current. Okay, and the information also processed there. It is also happening at the charge level. Why are we not calling it a quantum? Please remember, when it comes to realization of memory in the case of classical computers, or processing in the case of classical computers, even though it is processed by bit, please see, to realize one single bit, how many charges are being used. That is a very important factor. So for a classical computer, billions of charges may be used to just realize one bit. But when it comes to quantum, to realize one single bit, let's say a bit of quantum superposition state, that is a qubit, is done using what? A single atom or a single ion or a single charge. Okay, at the most few charges when it comes to quantum dot, but not in billions. So that's why this is becoming a quantum computer, that is becoming a classical computer. Means classical in the sense macroscopic, large compared to micro, it is going to be very large quantity. Okay, so definitely we will talk in terms of existing NISC era, where are these devices are being implemented or used. Okay, so the existing industry infrastructure, if we see, it is already, when it comes to semiconductor industry, it is matured. The mission of semiconductor mission, it is a decade old. So there's a lot of manufacturing units when it comes to semiconductor chips. It is being explored, and it is already almost matured. So that means only thing is I have to tweak a little bit here and there and just come up with few charge based qubits. That way it becomes more quantum, and then I can connect to existing classical chips to do a hybrid computing. That is possible in the case of semiconductor platform based quantum technology. Okay, now let's see what kind of a materials are being used to realize the semiconductor qubits. Okay, as we are looking for a survey, we better know it. Okay, number one is silicon, right? Gallium arsenide, germanium, silicon, all these things are the group, the other things are belongs to semiconductor materials. You see, the isotope of silicon, okay, which is purified to silicon-28 isotope, which can, by that process we can eliminate any nuclear spin noise, fiddling with the electron noise. I don't want. I will have my external magnetic field fiddling with the electron. I don't want spin of the nuclei coming to the picture. For that we can do some purification and get some isotope. You see, you remove the protons, you are going to get what? Different atomic number based element. Okay, but you can play with other possible changes in the system. Probably you may work with adding neutrons or removing neutrons. In that way, what happens? You are going to create an isotopes. So those isotopes can get rid of the nuclear spins that may fiddle or that may disturb the electron spin, just we saw earlier. Okay. For example, the silicon isotope 28 is being used for qubit realization. Gallium arsenide, in fact, it has a very good high mobility charges and very strong spin orbit coupling is there within this. So when it comes to interaction, this may be a good resource to use. When it comes to spin system, it is spin is generated out of the orbital spin, not the individual electron spinning on its own axis. No, it's an orbital spin. So orbital to orbital spin interaction, let's say I want to have one qubit of one atom to another qubit of another atom realized out of this electron. So when it comes to gallium arsenide, another superconducting material, orbital spin to orbital spin interaction is very, very strong. So in that way, I can take care of not knowing to bother about whether the interaction is there or not, because it is going to be very strong as per the structure of this gallium arsenide material itself. Okay. The next one is silicon germanium. You see, silicon and germanium are trivalent and pentavalent materials. You know what is trivalent is they are supposed to have four charged electrons in their group, in their atom. Means one electron is they're ready to accept. In that by way they will become a negative charged ions. When it comes to the pentavalent, they're supposed to have only four charges, but they have five charges. In that case, what happens? This guy is ready to donate and become a donor. So these two things are happen to be, one of them is trivalent, another one is pentavalent. So this is the silicon and germanium. If we have combination of them, the heterostructures, what you can come up with, you can create something called quantum wells for a spin confinement. Okay, so let me quickly tell what is the spin confinement using wells. We will just use our classical analogy to understand. Let's say somebody is going in a road in the night, they did not say, okay, there is a well. Okay, so by mistakenly they fell in, So the person is going to be inside. Okay, unless somebody comes and helps him to come out, because there are no stairs, it is too tall. So the person is not able to climb because he doesn't have any energy, or you can say he doesn't know how to climb. In that case, the third party has to come and give the energy. How much energy? Whatever is the height of the well, that much energy he has to give. In the case of quantum, the same problem can be said as some kind of a quantum well is created where a charged particle, like say, let's say spin silicon germanium based qubit, right? If it anyway is a spin qubit, it is going to fall into the spin qubit. Means it is going to have a least energy state. To come out of that well, it has to acquire a large amount of energy from somewhere outside so that they can jump out of it. Now the question is, what is a confinement? Confinement is the moment you take this pentavalent and trivalent atoms together inside a same kind of a host. Sometimes what happens, right? Say now a simple strategy I'll tell you. If there is a positive plate here, okay, electron is attracted towards that plate. If I put another positive plate, okay, that is also attract. Okay, so this is how I can make the electron to stabilize in some location by putting electrodes. Okay, in this way, by all the directions, I can induce some electromagnetic fields and make the charges not to go anywhere, confine them. You know one thing, let me write down. If there is a charged plates, okay, if there is an electric field E acting from positive to negative plate, if I put an electron of charge Q, the force on that electron is going to be Q into E. In this case, it is minus E into E. It's an electron. Okay. Now, by any means, if the electron started traveling with some velocity, this time I'll put a magnetic field exactly perpendicular to the paper. Let's say magnetic field is perpendicular to the paper going into the board. So magnetic field going into the board, into the paper, magnetic current is there, means charge flow is there. In that case, you know what happens? Lorentz force means a magnetic force is going to be generated, which is going to be V cross B, means it's going to be perpendicular. In this case, charges goes downwards as they experience the magnetic force. Now see, by putting multiple magnetic field direction, multiple field strengths from different directions, by putting electrodes like electric plates here, I can make charge not to go anywhere by balancing all these electromagnetic forces. So this is the confinement. Basically, what you are doing, you are creating some kind of a hill or a well and pushing things to fall into that, to come out of that. So they should have energy more than this hill. So I have created some kind of a hill within the material. Okay, sorry, well within the material, where by any means if the charge falls into it, it is not going to come out because it doesn't have energy. So I can make the spin to fall into it, spin system. Now this is what the spin system, like wells are usually represented in quantum system. Okay, where this well technology, the idea is coming is, so the well is existing between x is equal to 0 to x is equal to L. Everywhere else potential is infinity. Only inside the hill the potential is 0. This is what the well is. Initially in quantum mechanics, people starts about step function, like what is this, a hill. Okay, it's a step function. The potential is infinity, potential is 0 here. If I send an electric charge or electron, in terms of put an electron on the other side of the the infinite potential, you know what happens? We assume that to go a traveling electron onto this potential of infinite or into the potential, it's supposed to have energy to cross into that domain. Okay. So interestingly, when it comes to quantum level, there is no need of electron to be there on the other side as a particle. By behaving like a wave, it can go into the material, into the potential. Same story. If I have, instead of a step function, I will have a hill where this is infinite, there is 0 and 0. This time, if I project a photon, sorry, electron, and whose wave function is represented like a wave going into that hill, it hits it, okay, it hits it, and then diminishes, and then as it exits, it expands. So basically, some kind of a truncate mechanism, energy absorbing kind of a mechanism is done by this hill. Why it is happening? Because electrons as a material not supposed to travel through the material, but as they are existing individually at a quantum level, where they are going to possess a lambda d, de Broglie wavelength is equal to Planck's constant divided by mass into velocity. So this is how, even the potential is infinity, electron can show its presence in the form of its wave function. So in the step function it is there, in the hill function it is there, even in the well function it is going to be there. What is that is? By any means, if the electron is in terms of its spin fell into this energy where external means is absolute zero. It's difficult to have absolute zero. You see, the ambient temperature around can disturb the system and give the system energy to even go somewhere which is not in our required zone. So here, if you see, if the electron wave function is something like that, it can exist even on the infinite locations, potential wise. But in that way, there is some non-zero electron presence on the infinite case also. But you see, compared to the inside and outside is very minimal. So this is how we are going to confine the electron spin into the well. So that's why it's called one-dimensional potential well. Okay, probably I might have applied electrodes on the one direction side, in the x direction side. If I apply on the y direction, if I apply magnetic field on the z direction, various directions I apply, I can make the electrons and charges to confine in their specific state. Okay. Now, that is silicon germanium heterostructure quantum wells, diamond NV centers, which are supposed to have a long coherence time at room temperature. We will touch them. We'll just discuss them little in detail. Okay. And next one is indium arsenide. This is also another semiconductor. Basically, you can prepare a one-dimensional semiconductor by drawing a wires, nanowires. So these wires are going to create something like, as you drawing the wires into nanostructures, the internal arrangement of the atoms inside going to become some specific topology, like they call topology, the different kind of a structure, systematically arranged. Okay, so by doing some external pressure, I might change the topology. So basically, these topological materials going to have the behavior of them is going to change depending on their topology. So in that way, we can realize a qubit out of it. So this is a nanowire indium arsenide based topological qubits. Okay, right? So very good. So one basic question here is asked: can you please explain the spin? Because general perception of a spin is different from spin in the case of entanglement. Okay, so the spin needs to be understood from the electron being rotating in an orbit. If the electron is, let's say, rotating in a anti-clockwise direction, sorry, clockwise direction, so it is rotating. It's just like a wire A DC current, negative charges are going in a clockwise direction, which means in the anti-clockwise direction, the current I is going through, DC current. Even one electron is also traveling. It's like a current carrying loop. So if I cut the loop, just for my understanding, I put it into straight line, it is going to have current flowing from down to up. Okay, so it is going to constitute magnetic field around. That magnetic field is there everywhere, right? In that case, the magnetic field is also there everywhere in the loop. You see, very interesting thing is, inside the loop of this current carrying orbit, the magnetic field just adds up magnetic fields. But outside, they just nullify. One component magnetic field is nullified by exactly opposite component on the other edge, other semi quadrant, semi. So this location is their magnetic field is exactly cancelled by the other side. So basically, there will be no magnetic field outside the loop, current carrying loop. Only magnetic field is there inside. So basically what I see, if I put it into like a kind of two-dimensional thing, if the loop is like that, so magnetic field lines would be like this. So what is this? It exactly looks like a small bar magnet whose magnetic field lines are like this. Okay, going out and coming in the south pole. You see, this is a magnet created by what? Electron rotating about its orbit. Okay, not only that, inside the atom, nucleus also rotates on its own axis. What is happening? It is also constituting its magnetic moment, north and south. It is also having its external magnetic field lines. Okay. Now, if you see within that magnetic field, the small bar magnet of electron is there. And magnetic moment is realized out of rotation. Not only that, electron can also rotate on its own axis. Another small magnetic momentum is created. So there is two spins associated with an electron. One is orbital spin, rotating due to rotating about the orbit. It is going to constitute a magnetic moment. That is a small bar magnet or a compass. Similarly, it is going to constitute a magnetic moment due to its own spin. Probably it is a small quantity. Yes, it is going to have. You see, this is smaller entity. This is a larger entity, the orbital motion. Okay, this is a larger, and probably nucleus would be little larger because it's a huge positive charge. It is rotating on its own axis compared to electron. The size of the orbit, the nucleus is very high. Okay, so you see what you are seeing. There is a very large magnet. Magnetic field lines are there. Within that magnet, I have one more magnet. If the magnetic, both the lines magnetic fields are arranged in the same fashion, you know what happens? As you can see, like poles always repel, they don't attract. Which means if the external, if the north and south pole wise the same way electron magnetic moment is arranged, in that case their field lines are opposite. You know what happens? The N and south tries to arrange in opposite way so that they can match and just get attract and just meet with the nucleus magnetic moment. So in that case, what happens? It just starts rotating. If I write down that or show it as small compass, north and south, the compass just rotates, just aligned to the external magnetic field. That is how people do navigation, by rotating the compass, okay, and seeing in which direction earth magnetic north and south are pointed. So the geographical north and south are slightly tilted when it comes to earth magnetic movement and magnetic fields, are north and south pole of earth magnetic movement. Okay, so the spin here is the magnetic field created or magnetic movement created due to some electrodynamics, some electric motion, electric charge motion. It could be rotating on the orbit or it could be rotating about its own axis. Okay, when it comes to rotating about in its own axis, you know what happens? Where is that figure? Okay, yeah, let me take this figure itself. Let's say the orbit size is radius r, the magnetic moment mb mu b is equal to, well, let's say a single charge q electron is rotating, q by t, how much time period it takes? Some t to make one rotation. This is current. So let me write down that as a current multiplied by area of the loop, not the circumference, pi r square. So area of the loop. So this is going to give the units of magnetic field. So that is what magnetic moment. Okay, just like a small bar magnet. So why it is called a spin? If you say, if I see this quantum particle of the electron, forget about its orbital magnetic moment, see its spin moment, its own axis, about its axis it is spinning. Due to that, it is creating a small tiny magnet. If you try to see whether it is pointing in a particular direction at a given time, that bar magnet, sometimes it is up, north south, sometimes it is south down, north down. Why? Because of ambiguousness at a quantum nature. So that's why the sometimes the bar magnet, sorry, sometimes the compass of this electrons, sometimes it is like this, sometimes it is going to be opposite. Okay, rotates. It keeps spinning back and forth, just like electron going back and forth between 0 and 1. Due to that, they are calling it a spin, electron spin, nuclear spin, electron orbital spin. Means it is spinning, changing the direction. If something is rotating, it is going to constitute what? Angular moment. So something is rotating, it has a linear velocity v, a translation velocity v. If you multiply linear velocity with a mass, you are going to get linear momentum. Then you multiply the radius, a dot product with cross product with the linear momentum, you are going to get angular momentum, which is pointing towards the surface. Means the rotation would be shown with some fingers, some would show angular momentum. So just like electron revolving around an orbit is going to constitute angular momentum of that particular electron motion along the perpendicular direction to the axis of the disk of rotation. Just like a bicycle wheel or a vehicle wheel is rotating, angular momentum is pointed exactly perpendicular to the wheel, and it always tries to stabilize. It is always tries to stay straight, not go wobble. So that is the formula, that is the background in having bicycle study wheel when you are riding it. Okay, so that is what the spin of a electron and its magnetic moment, whether it could be rotating or it can be spin, or a nucleus also going to have a spin moment. Okay, right? So I hope I cleared that. We remember that electron orbits around the nucleus, but motion around its own axis is new. Yeah, just like Earth is rotating about the sun, it also rotates on its own axis, right? So it is the idea. Okay, right? And in fact, it is a fact. The same kind of a nature is there at astronomical level, solar system, okay, and even at a tiny atomic level also process is there. Okay, so what is a spin different from orbital motion? Like I said, the spin of magnetic moment, sometimes it is north and south, sometimes it is south and north. The changing is, that changing is called a spin. Okay, right? So yeah, Dipanshu is saying all fermions like electrons are spin of particles. Very good, that's correct. So if you just segregate the particles and calculate their spin moments. You can find out what is the magnetic moment, like a value of that spin, the magnetic moment we just calculated, which can be expressed in terms of units of Planck's constant. So in that case, what unit of Planck's constant magnetic spin is there if you calculate? Interestingly, there are particles which are spin half, like 1 by 2. Some of them are uh, another fractions like a 3 by 2 or 5 by 2. Like that, various fractions are there. But wherever there is a spin of particles are there, they are going to call fermions. Okay, they show something called Fermi Fermi-Dirac statistics. They are going to satisfy, and the particles like a photons, you see, very interesting. They are going to have the spin in the integer form. Okay, they are not going to have a fractional spin. They are going to have integer spin. See, photons doesn't have mass. How can they spin? So you can see the spin, the nature of the spin of the photon when it interacts with some particle, exchanges that spin nature to the particle. That is where we see the spin of the electron. Okay, right. So fine, the Fermi-Dirac statistics, Bose-Einstein statistics are a BCS theory. Okay, so in that you people will be getting across various statistics, how to understand the particles, whether it's a flying qubits like photons, bosons they are, whether it's the electrons which are fermions, the stationary qubits, we can study or we can understand in detail. We are not going into the more further details. Okay then. So can we suppress the ambiguity by supplying magnetic field? Okay, Rajesh ji is asking. Please see Rajesh ji, the ambiguity is actually a superposition. If I don't have that ambiguity, it's like if I have a coin being tossed, during the flight I see ambiguity of head and tail. That is the superposition state for me. In that state, superposition state, pair coin be there in the head state 50%, tail state 50%. Okay, so that is how we will needing to have ambiguity. If you remove the ambiguity, you are not going to have a quantum superposition state anymore. Basically, like you are catching the coin, it is falls to zero or one state by force, which is classical, by the way. Means it is 100% exist in the same state. With certainly, such thing should not be there when it comes to quantum nature. That is ambiguous state. So there is no need to suppress. If you are suppressing it, probably you can do it at the end while measuring the system. Okay. Quickly, we will go further. We should not waste more time. So various different materials needed are used when it comes to semiconductor based qubits. Okay, right? So this material choice determines the spin coherence time. Okay, what is the spin coherence time? How long the superposition state should exist? How long this flipping should exist? That is the superposition state for me. That is decided by what kind of a material, in which neighborhood it is there, in which host it is there. In semiconductor, there is a host and there is a impurity. Okay, somebody hosted, the impurity is hosted by some host, that is what there. So those two things would decide what is the lifetime. And there is something called carrier mobility. Sometimes the electron is removed, this atom become a hole, a positive charge. That charges goes and travels somewhere, mixes up somewhere. So they may create something else somewhere. So this is a mobility of charges, you see, that is also going to decide how well I am going to realize, how good qubit I am going to realize. Okay, and also how many defects I am going to create. Means if I have a pure semiconductor material, I'll dope with something else into it. If I have trivalent, so if I have a normal semiconductor, I'll dope with a trivalent. What trivalent does? It extracts the electrons and it becomes an ion. In that way, it creates holes. So in the trivalent system, electrons being attracted, holes being created, holes are going to be majority carriers. But when it comes to pentavalent atoms, electrons were donated. So the electrons are going to be a majority carriers. So existence of what is the percentage or the density of the carriers is going to decide how good qubits we are going to realize. Okay. You see, just like any semiconductor, even semiconductor qubits also dictated by the nature of semiconductor materials. Okay. Coming back to the application, somebody was asking earlier, I think Lakshmanaranji is asking real world NIST scenario, where exactly these qubits were realized, how it is realized. Okay. Very simple. We just saw earlier a well, one dimensional well is created where the spin of the system is confined. You mean it exists between ground and excited and oscillates between ground and excited with a particular frequency. So that frequency is exists at the very bottom of the hill. To go to little bit higher level, like a different high energy, the spin it has to acquire the extra energy that is not there. So it has to just stay back at the ground level. Okay, such a thing I can create even on the other dimension, like a x dimension as well as y dimension. So I'm going to create a two-dimensional quantum well where it's like from every direction I put the charge plates, so the electrons are confined within that location. They are not supposed to go anywhere, they just confined. If needed, I will use a magnetic field also. Okay, fine. So that is one way of doing. Earlier I was talking about one dimensional. What is that? It is simple nanowire. You see, nanowire means very much close to having single electrons or the single atoms in a given wire, given stream. Okay, right? So if I do it on the surface like a graphene, right? Graphene, what is it known for? On a graphene layer, almost close to single atoms are there on a layer. Okay, that much thin the graphene layer is. In that case, the electron is confined to move anywhere on the two-dimensional surface. That also can create some kind of a qubit for me. Okay, if I by any means I realize a confinement of charge in three dimension, so that is going to be a quantum dot. And one charge confinement or multiple charges confinement, you are going to create a bunch of quantum dots. Interestingly, what they do is see how much area you are confining, that is the size of the quantum. This size of the quantum dots, if I just carefully see their energy structure, the band structure, what happens is if I have a single atom, what you will have, there is a valency band, there is a conduction band in the case of semiconductor material. If the electron is raised, okay, right, electron from the very much ground state to raise to valency band, okay, and then from valency band it goes to excited state, you know what happens? There is a positive hole is created, there is an electron is created at the conduction band. Okay, so there is like a separated dipoles kind of a thing. Now they can exist apart for some time. If I just take a one atom in the context, I'll have such things. If I take a many atoms in the context, put many charges in the excited state conduction band, many of them together, you know what happens? One electron influences the other one. So it's like a mutual effect. Their orbits, which are supposed to be a specific orbits, they will be no more specific. They split into the other orbits, like they may go slightly shift here and there. It is going to create a continuous band of structures. You see, valency band continuous, conduction band continuous. And if there is any charge has to go from valency band to conduction band, in such scenario, they have to have some energy of transition. Okay, now you see how many such charges are the atoms I am taking into consideration to confine the certain number of charges. if I certain, let's say some 10 electrons are confined, I might get some kind of a quantum dot. How can I differentiate it? I shine a light onto that quantum state. So the atoms or the electrons in that quantum state excite and they de-excite, they emit the light. That light is going to be red color. So another one is green color, depending on the number of charges inside a confined metal. Another one is blue light. So basically, by increasing the charges, you are going to create a larger atoms, the larger quantum dots. I'm sorry. So those quantum dots, their unique nature is depending on the size, they will interact or respond to particular kind of light. I shine a white light, I'm going to see a reflection of a transition of blue light in a particular quantum dot as it goes the size. Okay, right? So there is a question here. Graphene is a 2D material. Yes, absolutely. Okay. So there is a question, are real-time applications of spin are there? Please provide. Yes, spin-based quantum qubit is being realized. Okay, that is in the case of these things only. Okay, right? Or you can do ions. Okay, ion traps, or forget about trapped ions. There is something called NMRI, nuclear magnetic resonance. NMRI. What they do, nucleus spin is there, right? Nucleus, positive charge spin. That can be fiddled, changed by external magnetic field. So they take some kind of a solution, they add some solvent into it. So there the molecules may have the nucleus which can be having particular large magnetic moment, which can be arranged in a particular direction. If my external magnetic field will be some kind of a fluctuation, this magnetic moment can also be fluctuate. With what frequency they fluctuate? Okay, right? What we can do, from the external magnetic moment, I can make it to fluctuate. We can calculate how much frequency of oscillation of fluctuation. If the magnetic moment is pointed in different direction than external applied magnetic field, you know what happens? You see a precision of this magnetic moment about the applied magnetic field. So knowing the precision frequency also, you can find the nature of applied field or nature of the system. Okay, so that is what the idea was used in the case of MRI. They see the body fluid, how they respond in terms of their magnetic movement in response to the applied magnetic field of that huge coils, electromagnetic coils are there in that MRI machine, we say, or even in the CT scan. Okay, that is computerized tomography. Here it is nuclear magnetic resonance. Okay, right. So the application is that one, MRI. And when it comes to, okay, so let me see a couple more questions here. Can glassy based material create the qubits? Yes, definitely. Glassy based materials are going to create, especially the glass materials like which are transparent, known to give. Okay, they, if they can make a nonlinear crystals out of them, they're known to give entangled qubits coming out of them as a photons, which means inside them there are stationary qubits. They're going to become entangled probably, and that entangled nature is carried through the photons. So in that way, if you can understand, you can appreciate how these glassy based materials can create a qubits. Okay, right. So the next question is, uh, uh, yeah, how engineering materials are different from quantum materials? What is to be said in layman terms? Okay, simpler terms for easier visualization. Simpler visualization. See, like I was telling you earlier, the engineering material is done at macroscopic level, large level. Just to realize a single bit, I use so many atoms. But when it comes to engineering quantum materials, For quantum technology application, I'll work at a single system, at the most few bunch of electrons in the vicinity, in the confinement to create a quantum dot. So that itself still existing at the quantum regime or a quantum limit. Okay, fine. So please suggest some materials used in photonic applications for efficiency improvements, especially in 2D nanostructures. Okay, so you can check some quantum optics people who are working on photonic applications. Okay, and when it comes, okay, you are asking for photovoltaic applications, right? Okay, for photovoltaics applications, people who are working for better solar panels, you can check on their research groups. Okay, so if I find some, I'll definitely share. Okay, right. Okay then. Yeah. Any other question? Yes. Please explain quantum dots. We'll getting to the details. Okay. Gallium nitride. Yeah, it is another kind of a material which we can use as a host to create a qubit. Can it is be used in quantum? Yes. If it is happen to, if any host is a super semiconductor material, that is a very good the means to realize qubits for me. Okay. Right. So we are almost crossed 1 hour 10 minutes. So what we'll do before getting it the quantum dots, we'll quickly take 5 minutes break. So meanwhile, I'll just put up this slide open. You people can just stare at it, and we'll just come back at 4:15. Yes, welcome back everyone. Okay, so there is a question, follow-up question asked by Keshavarji. Can gallium nitride could be used for quantum qubit realization? Yes, possible. How? Yes, it has to be doped. Some kind of a donor is required to have the electrons to realize some kind of a spin qubit, right? So, and Rajesh, you were saying rare earth atoms are rare earth ions, they call. Yes, they're very good materials, especially to realize a long coherence time based qubits. You take a rare earth ions like yttrium or erbium, you dope with some other rare earth ions into them, then you can realize a long coherence time qubits. So the group where I had happened to work in Sweden, they were using this rare earth ions to realize a quantum memory in the optical cavities. Okay, right. So what is this color emission when it comes to when it comes to the quantum dots? Okay, so that is what we are going to discuss now. And the other question by Gopiji is asking, is that every material will show quantum confinement effect if they are reduced below their Bohr exciton radius? Probably yes. Yes. What you are saying is quantum confinement effect if they are reduced below their Bohr exciton radius. Uh, See, you mean to say within the atom? No. Let's say I have a nucleus and the electron which is taken out. If that electron is going to there somewhere, there is another nucleus without any electron, there is another nucleus without any electron, another nucleus without any electron. So on the four sides the nucleus is there, all of them are attracting with same force. So it's like a stalemate. So I can have this electron being confined. So what I will do, this one will be some kind of a donor atom, means impurity. These things are like a host. So in that way, what I can do, I can make this donated electron to confine in the host material. Okay, not just a single electron. I can take a bunch of electron confined into a location. So basically, you see, the quantum systems exist at multiple energy states. Okay, so there is a quantum physics. To understand any dynamics, the first thing people call it discuss is particle in a box. That is the first problem going to be discussed in quantum mechanics or quantum physics. Okay, so don't worry what it is. If I give analogy, you will really understand. Let's say I have a box, mass m. If there is a force F, it is going to have an acceleration. So what is the dynamics? How can I represent the dynamics of the system? F is equal to m into a. Mass is equal to, sorry, force is equal to mass into acceleration. So this is the equation which is going to tell me how the dynamics of the system is evolving in time. I can do F is equal to m into second order derivative of time position, and then if I solve for a given force, I am going to get what is the position of the object at every given time in terms of given force, which is scaled by the mass. If the mass is more, probably the rate of change of position may be not that rapid. Okay, so in a classical physics or a classical dynamics, I use classical laws of physics, which is Newtonian laws, Newton's second law, right? This is a Newton's second law. Similarly, if I have a charge of mass electron, mass of an electron, if I keep it on a table, since it's so tiny, I want to specifically see this, I'll put it in a box. So this is called particle in a box. This is so tiny, it can take energy from the surroundings. So I have to make it vacuum just to see its nature. Okay, it goes here and there. If I still, even in the vacuum, it goes in there. If I make it 0 degrees Kelvin, absolute zero, let's say. In that case also it goes here and there. What is this? This is, it comes with some internal energy, 0 point energy. Why is that so? To understand that, we have to treat this like a wave. At quantum level, things are no more like a particle material. They become a wave. When it becomes a wave, it is going to satisfy a Schrodinger equation, which is h psi is equal to E psi, where psi is a wave function, h and E are the operators, quantum operators. H is a thing which is equal to total energy of the system in classical physics, total energy, right? Okay, where E is energy with which system can exist various ways. Okay, so Hamiltonian would be simply equal to kinetic energy Hamilton operator plus some potential energy operator. Right? What is the potential energy? For example, we just now we talked about electron is being confined by 4 nuclei. See here, it is confined. It's like two-dimensional well I have created for the electron. So electron should not go anywhere within this well. It can exist in the well, it can't go beyond the well. So that is some kind of a potential is being created. What kind of potential? Probably electron is there. There is a positive charge on the left, positive charge on the right. So there is no possibility for electron to go anywhere in the direction. Let's say by one of the charge I remove, electron starts going left. If I remove the other charge, it may go to the right. Let's say I don't have any charges at all inside. So in that case, electron can freely move here and there. So let's say the potential is zero in that case. Only kinetic energy is there. So H psi is equal to E psi, kinetic energy where P is there, which takes a differential equation operator form, which is going to be P is actually minus IH cross dou by dou x, differentiation with respect to x partially. So this is the x component of linear momentum. So if I solve the dH acting on psi is equal to E psi, you are going to get a differential equation, second order differential equation, which is something like okay, plus omega square psi is equal to 0. Okay, where omega is square root of k by m, propagation constant divided by m. You see, what you angular frequency omega is there connected to wave propagation vector, where wave propagation vector is 2 pi by lambda. So particle is going to, electron is going to have a wave nature, something like that, and its corresponding to wavelength will be there lambda, that is de Broglie wavelength, that is connected to the propagation vector k, and mass is there anyway for the electron. So if I solve this differential equation, it is going to exist with various possible boundary condition values if I substitute. So this electron can have various possible wave natures. One is like this, another is like this, another one is like this. So this can exist with some energy E0, E1, E2, okay. So on, so many possible values, okay. So the electron just inside a one-dimensional box can exist with various energy wave function states. So that is how I am going to understand what is the nature of the electron inside a one-dimensional box. So that is the first thing comes into the picture. Next thing is particle in two-dimensional box, that is the well, and then also hill. So it's very important to know them to understand things. Now, when I have such a thing, the electron can exist either this state, it's like a ground state, or this state, excited state. Okay? By any means, if the electron happen to have more probabilistically on the ground, if I supply some energy, it can go to the highest energy more. After some time, it has to come down and emit the radiation which is accepted in the first place. Now I'm not talking about any single electron anymore. I'm talking about many electrons confined. How I'm going to confine? I'm going to add some kind of a charges around, some kind of a electrodes around. Electrons are going to confine, starting with a single electron. Now that electron can have a ground state and excitation lies, and when its energy is some energy is supplied, it absorbs. After some time, it emits. It is going to emit depending on the number of electrons confined. It can emit red color, green color, or a blue color. Okay, so more charges is going to emit more energy, right? So that is how simple. So the blue color is highest energy, red color is the lowest energy in the spectrum. Okay, so that is what the quantum dot for us. Just like collecting all those things, electrons in the same confined space. Okay, right now, based on quantum dots, the applications, people can work with solar cells, make a solar cells, better solar cells, and biomonitoring. You see, this quantum dots liquids you can create. This liquid, if for the if I don't shine a particular light, because if I don't shine light onto it, it remains transparent. The moment if I shine a light, okay, depending on the size of the quantum dot, I see a particular color. So what you can do, okay, if you want to see how the medicine is traveling into the body of, let's say, human body or any biological, you can put these quantum dots into the medicine and then give the medicine to the either some kind of animal or somebody, and then you can track the color, how it is traveling. Okay, in that way it can be monitored. Okay, and the same thing, you can use this quantum dots to create a drugs and gene delivery. So it's an application from the medical, from the diagnosis. Okay, and you can make a sensors. There is some light coming out from some laser which you can't make out from your naked eye. What is the energy coming out from that laser? You can use the sensors out of quantum dots. They respond to that particular color, and if I have a combination of all the quantum dots in my sensor, what kind of a color it gives, accordingly I can measure, I can just calibrate what color of laser is coming out. It's like a litmus test. Litmus test giving the acidity of the chemical. Okay, and photocatalysis. Catalyst is something, you say, catalyst accelerates the action chemical reaction. Catalyst is very important to create products out of some raw materials. So to accelerate, they add some catalyst. Okay, right? What you can do, you can add the catalyst in the form of some quantum dots, which can act, and which type of quantum dots to coming to the picture, I can shine a light. So only particular size quantum dots are going to come into the picture. So that is a photocatalysis. Okay, so that is what, only for the sunlight we see particular blooming of flowers and particular growth of flowers, okay, and trees. So light emitting diodes also you can make with this quantum materials like quantum dots. Okay, so when it comes to qubits, very good, there we can confine, realize a charged qubits with a ground state and excited superposition. And the key properties here you see, discrete energy levels you can realize, basically it's like artificial atoms for us. And the quantum dot shows a quantized orbital energy, just like energy, electrons energy is there in the orbits. Okay, the same fashion there is a quantized orbits, means together some fixed quantized energy states I am going to see. Those are very much discrete. From there I can realize a qubit, and they are tunable as we confine the confinement can be tunable. The same fashion, okay, we can use some gate voltages and adjust a dot size and the number of electrons confined. We can play around with what kind of a quantum dot, what kind of a qubit I want to realize. Okay, and you can have a very good control using some electric pulses. As you know, everything is electric here, electronics here. So electrical operations enables and fast and scalable control you can have with this kind of a quantum materials. Okay, right? So quantum dot qubits could be spin up and spin down, and like earlier I said, the quantized orbits, right? Let's say one single quantum dot probably have just a ground and excite. Many, if I have, one of them will influence the other one, right? So because of that, probably the ground state is going to split up into multiple states. The excited state is going to split up into multiple states. Okay, initially there is a quantum dot is placed in the ground state. Now it has a three possibilities to stay anywhere. Okay, so I can pick any one of them as my ground state. I can pick all the three of the excited states as a triplet states they call. So that is what a singlet to the triplet. I can ensure that the ground state is only one singlet state and the excited state is triplet, yes, and triplet state. Okay, so this is how we can realize a two electron two bit. Okay, right? One of the triplet, one of them we can have as an excited state. Okay. So this is a quantum dot qubit, and there is something called charge qubit. Means we can encode the information in the charge position of an electron across a double quantum dot. Okay, two quantum dots are there where this charge is placed in this kind of a situation. From there you can realize a qubit out of it. Okay, right? Whether the charge is there confined in this electron, so in this quantum dot or in this quantum dot. So I can fluctuate between this, just like we juggle the ball between two hands. That way we can realize a quantum dot qubit out of it. Okay. So advantage, as we saw earlier, electrical control, compatibility with semiconductor processing, because semiconductor material plays with the charged electrons and positive charged holes. Okay, right? So these are potential for large scale integration because they can connect with the semiconductor devices. Okay, the silicon spin qubits, 0 could be downspin, 1 could be upspin. We can make them to have a superposition. At a given time, it always fluctuation. How can I create? See the electrodes. Okay, so there is a lot of electrodes are involved. At the end of the PPT, I have given the material, sorry, this reference, you can check it. Okay, see, it's like a CMOS FET. I have various gates and various silicon dioxide substrate, and silicon is there, metal oxide is just like silicon. Okay, silicon dioxide, and then you can have some kind of a potential is being created for the electron spin to exist as a upspin or a downspin. So basically you are creating two hills. If the electron is there upspin, it is confined, it can tunnel through to go to the other side, become downspin. How can I do that? I can make an application of the electromagnetic field. See here, B is applied, the magnetic field is applied, and electric field is applied perpendicular to it. I can give energy for this electron to tunnel through left to right, right to left. Okay, so how did we apply external magnetic field? And electric field you can apply through microwave pulses. Okay, right? So the electrodes, all the connecting things are given here. The experimental how it works, that is used. Okay, so nuclear spin based system in the case of silicon, it is going to have very good coherence time, more lifetime. Okay, it is compatible with CMOS FETs. Okay, complementary metal oxide semiconductor FETs. Okay, right? The donor qubits in the silicon, there is acceptor and donor in the semiconductor material. So here the qubits are going to formed with the donors in the case of silicon. Let's say pentavalent material if I take, which are like phosphorus. Okay, right? So dopant atoms, if I just take, they can embed in silicon crystal as a naturally occurring qubits by offering two independent qubit degrees of freedom. They offer extra electron, they become positive charges. This positive charge can have a nuclear spin up or down. So that itself a qubit for me. Okay. So the electron spin qubit, nuclear spin qubit. You see? So electron spin qubit is just a single electron whose coherence time will be in milliseconds. But when it comes to phosphorus, okay, right, nucleus itself, which is after donating an electron as a donor, it can have a coherence time very long. It's a very ideal for the memory. Okay, inside a host, the phosphorus can become a qubit by donating an electron. This ion can have upspin and downspin. You see earlier, the nucleus is having a spin. Similarly here, phosphorus positive hole can have a spin. Okay, right. Another one is NV centers in diamond. We talked a lengthy earlier in the very much introduction session. Okay, so what did we do there is we took a carbon nicely arranged. Carbon has various pack structures. In one way I arrange, I'll get a graphite. Okay, three-dimensional. And two-dimensionally I can arrange nicely well packed. It's a graphene. Okay, sorry, not graphite, graphene. Right? We can have graphene nanowires. Okay, and three-dimensional structure is diamond. Very strong, nicely packed. Now you remove two carbons out of it. You have two vacant carbon locations, just like holes. These are carbon holes. No? There are no carbons. Now nitrogen happen to be very close to that size wise, electrons wise, availability wise, very close to carbon. You dope the nitrogen into this carbon solid state structure. You dope in such a way, let's say 100 carbons you remove, you only dope with 50 nitrogens. Means there are 50 empty holes still there. 50 of them are nitrogens. So there is a vacant carbon place. It's called a, just like nitrogen vacancy, just like a dipole, a positive charge and negative charge. Nitrogen by nature and vacancy by nature can together form a dipole moment. Okay. Interestingly, this dipole is going to be seriously sensitive to the external magnetic field if they come near to this NV center. Why? Because you see, nitrogen orbital structure inside its atoms, the electron will have particular orbital structure, ground state, excited state, and so on. Okay. When I have a vacant carbon also something. Now what I do, I remove the carbon and have a nitrogen near to it. Okay. Now what happens? Nitrogen vacant positive charge location would interact. You know what happens? They influence their magnetic moment. They influence their orbital structures. You know what happens? Let's say there is two orbits possible for this NV center, or let's say single nitrogen. When it starts interacting with some positive charge or the carbon hole, it starts deviating from that structure. Okay. Once it starts deviating, then there is external magnetic field. That single ground state orbit would split to three multiple orbits. This is called triplet. And excited state also may get triplet. And by any means, if there is a NV center exists initially at the low level, that has three possibilities here. Now, this is the fine orbits which are there created, you see. They are exist with different spin magnetic moment. You see, ms plus and minus 1. And you see, the transition within the ground state from ms0 to ms plus or minus 1 can be possible with microwave applied pulse. Okay. And from ground there is a triplets possible. From the any of the triplet to excited state triplet, you see this is also triplet. Okay, from one of the triplet to excited state triplet, I can do that by incidenting a green light, higher energy. Green light is observed after the NV center excited. After some time it has to de-excite. When it de-excite, you see that time it may not go all the way down, it just falls down to ms plus or minus, and it emits only red color light. So you see, just looking at the red color light from the green coming out, what we can see, initially it's supposed to have no hyperfine splitting when there is no external magnetic field. When there is external magnetic field, that time you see the splitting has occurred. Okay, when the splitting has occurred, in that case the electrons no more fixed to one of the ground state, singlet state. The system is no more fixed to one of the state. It is possible to three triplet states. In that case, excitation is very much response to various colors. If it respond to green color, means there is an external magnetic field. If it doesn't respond, means there is no external magnetic field, because the incident energy doesn't match with the, there is this transition. So people thought, can't we use this, because this kind of a triplet transition exists at a room temperature, and it is very much respond to optical initialization, and this transition of this kind of hyperfine splitting exists for a very long time. So people thought, okay, we can use this to create a qubit. That is what NV center qubits they were using for a sensing. Okay, right? So moreover, semiconductor materials are used to create what? Single photon emitters. Okay, the moment you have a single photon emitters which are light based, you can create the sources out of it. Once you have a sources, you can create a quantum chips for photonic quantum computing. Means using a single photon sources, you launch through some optical fiber kind of a circuit, you use some beam splitters. You see, wherever there is a two streams coming from one input stream, that is a beam splitter for you. So you can create a what is called photonic chip using the semiconductor materials. Okay, so I hope I am trying to answer the questions which were asked earlier, the real world applications. Okay, so NV center material, the NV centers are seriously sensitive to the external magnetic field. They create something called magnetometers, which are going to measure MRI like imaging of magnetic field coming from neurons. Okay, we can even like a charge or the electrical activity from neurons can be measured with the NV centers. Okay, and the spin transition frequencies are temperature sensitive for nanoscale thermometer. Means we can measure the temperatures at a nanoscale precision. Okay, and electric fields. So Stark shift means we just saw magnetic field shift. Okay, similarly, if I apply electric field, again also fine splitting happens. From there also we can, using some spectroscopy, we can see whether the system is responding in presence of electric field or not. If it is responding, electric field strength is there, certain quantity. If not, it is not. So we can measure the electric field strength at a very fine, very minute level. Okay, using this Stark shift. Okay, so when it comes to theory, probably people will be discussing in detail. You are going to write a Hamiltonian of this NV centers or Hamiltonian of this qubits in the semiconductor. Just like earlier, we wrote a Hamiltonian with the kinetic energy plus potential energy. Similarly, you can write a magnetic moment of this Bohr magnet using applied magnetic field. Okay, and spin operator, S is a spin operator which rotates things up and down like a X orbit, sorry, X gate. Okay, so in that way you can write the Hamiltonian. In presence of the Hamiltonian, you can measure how system responds. Okay, and from there you can do quantum computing. and you can have interaction between the qubits. That is also one kind of information processing. So there is a spin operator S1, S2 representing two systems connected by some coupling is a J, right, coupling factor, and there also you can do some kind of a information processing. Okay, so semiconductor design challenges always obviously there. There is a charge noise. When I say a particular charge is confined by another some charges, means external charges are also there. They're also going to create a noise. Okay, and nuclear spin noise is also there. Fabrication variability, like sub nanometer variations is in gate dimensions lead to inconsistent qubit properties, requires precise lithography and post fabrication tuning. So since happening at a very minute level like a nanoscale, it is all based on the lithography, the lithographic. So you have to work very carefully. Okay, that is one of the challenges. Okay, so let me show you a quick into the other part, superconducting qubits. Okay, so we just finished semiconductor qubits, right? Semiconductor material based qubits, and then we'll get into superconducting. Wait a minute, let me, yeah, yeah. So again, the applications. What are the possible applications? Whatever were there earlier, sensing, computing, communication is also possible here when it comes to superconducting material. And they are known for zero electrical resistance for sure. Okay, in addition to earlier, this is something new compared to semiconductor. There the current is semiconducting, but here superconducting. Okay, there is something called Misner effect will come into the play here, where superconductor expel the magnetic flux from their interior to outer. Okay, if there is a semiconductor material is there, if I apply a magnetic field, so magnetic field lines will not go through it, they go outside. Basically, what is this effect is the semiconductor material acts like a repellent to the external magnetic field. So that is what the idea used for levitating trains, you see. Okay, right? So that also come into the play, Misner effect, and it is in a way collection of many class quantum level effects, okay, very close to microscopic quantum coherence. Okay, right? The entire condensate is described by single quantum wave function enabling qubit operation. Okay, we are not completely getting into the classical domain. We are just collecting many qubits or many charges together. Okay, or many superconducting material, many charge carriers together, like there is something called Cooper pairs. We are going to have a quantum effect like a superposition. So that is what we are going to have. Interestingly, that is have a very good coherence time. Okay, so like I said, Cooper pair, electron moves, stick together, appears to be stick together for a time being. Okay, so there is something they are connected to the phonon emission. You see, charges actually vibrate in their structure. So that vibrations are actually called phonons, right? So due to these vibrations, there will be a resistance in the system which can be reduced or like reduced by having a material in superconducting level. There, due to this phonon structures, electrons has to travel from, okay, very free locations to very narrow location. See, wherever they are free, they can roam freely. Whenever the narrow location is there, they have to go very close to each other. That is where they appear to be like a paired Cooper pair. Okay, this is a phonon-based process. That is something called pair attraction, and this can be described by BCS condensate, condensate. See, electrons by nature, fermions, when they combine, they're going to form a bosons. Okay, so these Cooper pairs are a macroscopic quantum state. They prepare long range order they have, and basically what happens if I create one superconductor, another superconductor, you put an insulator in between, you are going to have a sandwich. You know what happens? If you cool the system, the Cooper pairs are formed, they jump into the other side. Another Cooper pair from there also jumps. So they go back and forth. But for any group, if I concentrate, they're going to have particular frequency of oscillations. So on the left hand side, you have a particular phase of oscillations for the superconductor one. Another right side, I have a S2. If I see overall, it is good. Both of them are going to have a separate, like a phase difference, which is something like a phi, which is some kind of a flux in the magnetic field. Okay. So the current through this kind of a junction is depends on that flux factor. Okay. If the flux is zero, there will be no current. So they should be having some difference in these oscillations. Okay. And obviously the difference may come from when you apply external voltage to this Josephson junction. And there will be always some critical current about which or with which it oscillates, sinusoidal, okay, with a frequency of flux or phi. Okay. Now here there is something called AC effect or DC Josephson effect. Okay. So what most important for us to try to understand how we can realize the qubit out of it. Okay. So let me go straight away into that particular case. Okay. If I write the Hamiltonian for a simple inductor, I'll have a quadratic potential energy, quadratic kinetic energy. So basically, potential energy of, okay, 1 minute. Potential energy is simply half CV square. So kinetic energy, half CV square is coming due to half CV square coming due to capacitor contribution, and similarly, inductor is going to contribute half, half, okay, half, okay, and I square, that is Li square, where L is the inductor. So a LCR circuit is going to have a quadratic potential energy and quadratic kinetic energy. If I just connect to a battery, it's basically going to create just like a simple pendulum kind of a structure where energy oscillates between capacitor to inductor. But the moment I remove the inductor, replace with Josephson junction like this, Josephson junction by nature acts like an inductor, means Cooper pairs induce two more Cooper pairs. In that case, the kinetic energy and potential energy becomes different. You see, earlier the Josephson energy, inductor energy is just a EJ, you can say. Now it becomes some cos of phi dependent. At the same time, the kinetic energy is earlier half CV square. It becomes dependent on, okay, how many Cooper pairs were generated, N, okay, and so there is something to do with the structure of the material. All those things come into the picture. Hamiltonian now depend on the phi, the phase difference. In this case, if you see the nature of the curves of the potential or kinetic energy, they are sinusoidal in structure. What is this is? Earlier, the potential energy for an inductor is something like this, where the inductor and capacitor can exist in equal various possible superpositions, like that. Let's say 0 state, 1 state, 2, 3, 4, 5, 6, 7. In terms of capacitor, it's like 5 coulomb, 10 coulomb, 15 coulomb, 20 coulomb, and so on. Okay. But the moment I replace the inductor, you know what happens? This parabolic potential energy, you see, just like a ball, you have a ball, you put a marble, oscillations happens between 2 points. See, this potential is there. Now this parabolic potential, infinite parabolic, it is extended to infinity. See, this infinite parabolic potential becomes a sinusoidal potential. How? Right? You can just see this part of, some part of the potential is removed, that is bent into sinusoidal. Okay. Now there were states like 3, 4, 5, 6, 7. which were existing above 2, those also they are not removed, they are going to exist. You know what happens? Those are get compressed into the same region between 0 to 2. In that case, what happens? You are going to see unequal separation chance. This is just like equivalent to having real atom. That's why it's called artificial atom. Okay, so using Josephson junction inside a LCR circuit, replace Josephson junction, replace the inductor with Josephson junction. You are going to create what? Artificial atom structure with the existing states of n equal to 0, n equal to 1, n equal to 2, and so on, with some non-linear separation between these states, just like ground, just like ground excited, next excited, next excited. See, they are not equal. The transition states are always not equal. If I have simple LCR which are equal earlier, you see, all are equal. So that equality of linearity is reduced by adding the Josephson junction. So that is how people are going to create a qubits out of it. See here, the energy of the capacitor, energy of the Josephson junction means the inductor, and what is the ratio? What is the ratio place in the quantum computing? And you can use some circuit. It's called quantum circuit electrodynamics. You can control the qubits there. Okay, so you can have some control fields, external fields being added. So this is going to be understood using something called James-Cummings Hamiltonian. Okay, so you can quantize your Hamiltonian. What was the Hamiltonian here? You can quantize this Hamiltonian in terms of creation and annihilation operator. There further you are going to get some kind of a sigma applied fields, that is also there. We will not get into the details. Somebody who discusses in detail, they may explain it. Okay, fine. So as you know, some superconducting material works at cryogenic temperatures. Okay, room temperatures in a way it's not possible, right? Okay, so large scale connectivity is not that easy. That's why the scaling is being slightly hindered. Okay, who is using such qubits? IBM is using, Google is using, Rigetti is using. Okay, and how many qubits they realized so far? That is also given. In which year? Okay, that is also given here. And what kind of a coherence time, excitation lifetime, and further it is connected to the coherence time. Okay, what kind of a gates we can realize on them, how good gates could be, that is represented in terms of fidelity. So you can see that. Okay, semiconductor versus superconductor, if you have to compare, there is a comparison table. Straight away, the one most important is superconducting has to work at a millikelvin. Okay, right? So but semiconductor has a flexibility to work with little bit larger temperatures. Okay, few kelvins or millikelvins. Okay, right? So coherent times, microseconds, few microseconds when it comes to superconductor, milliseconds to microseconds range. Okay, so the emerging platforms where semiconductors are being explored, as of now, the superconducting is vastly explored. It's being mostly advanced. Okay, right? So qubit density is moderate when it comes to superconducting, and it is very high when it comes to nanoscale, and it's a very good integrability with the classical electronic circuits. Future is going to be a combination hybrid. Okay, so spin qubits will be used. NV center could be in combination with them, because wherever there is a possibility of not using a room temperature, there maybe can use NV centers. Challenges: decoherence, obviously for any qubits, scaling, connectivity, and these are noisy. Obviously, environment is coming to the play. You have to do a error correction. Okay, and the crosstalk between qubits is also a big issue that has to be addressed. If it is not removed, you have to do eliminate by mitigate by error correction. So the summary is superconducting and semiconductor are definitely a very good means to realize qubits. Looking at the percentage, superconducting is explored more, and semiconductor happen to be in a perception of macroscopic event. But if you confine to a very microscopic, you can realize the quantum dots and spin qubits. From there you can extract the quantum computation out of it. Okay, right? So whatever we discuss, temperature and challenges we discuss, that is mentioned here. I'll just give the PPTs to you with all these details mentioned. The references are mentioned at the bottom. You can just explore them. Okay. So with this, I conclude the survey of superconducting qubits and survey of semiconductor qubits. Okay. So remember, the superconducting are in a way the chip-based qubits, LCR chip-based. Semiconducting is charged qubits, like electron confined qubits, or electron like ions confined in a host, such qubits. Okay, so details when it comes to exact platform or a protocol will be done in the coming sessions by some resource persons. Okay, so let me take a quick questions here in the chart. Okay, let's see. Okay, so where did I stop? From that point I'll take questions. Okay, so I will go fast. There are quite a lot number of questions. Okay, so I answered a question on Bohr exciton 418. Why not engineering material? Okay, let's take this question from 418. Why not every engineering material cannot be quantum material candidate? What qualifies a given substance? Yeah, whether the substance is going to behave like a quantum mechanically or not is a question. Quantum mechanically means it has to exist in multiple states with different probabilities. Means a system can exist with various possible states with some probability P0, P1, P2, P3. You bring me anything which can exist in probabilities at different states. That is a very good means for me to realize a qubit out of it, superposition state out of it. But not every material is like that, because you combine many microscopic systems together, which are by nature microscopic, means quantum mechanically superposition state or quantum probabilistic states. When I combine them, they are going to nullify their quantumness. They are going to become a classical. That is where we lose the chance of realizing a qubit out of it or any quantum state out of it. So that's why not every material can be engineered into have a candidate for realizing a quantum computing. By nature, they can be used for some applications, but not for quantum computing. Okay. And the next question, like Ashok ji is saying, I'm working in the area of meta surface design for polarizers and sensors application. Which simulation software can I use to design quantum materials? Okay, so yeah, you're asking in depth actually. Like my specialization was during my PhD, I was studying atom field interaction, where the laser fields were interacting with rubidium atoms. That is those things I design using master equations. There's something called Lindblad-Blaster equation, where you use the density matrix formalism, Hamiltonian you define for the system of atoms and the interacting fields, and you make them interact through density matrix formalism and write a master equation. Master equation itself is a dynamical differential equation. Depending on the system, I took 3-level atomic system. Qubit is a 2-level atomic system. Qubit I took 3-level atomic system. Basically, it's like a higher order differential, like 9 differential equations are there. They're all complex. So the mathematical model which I took is a master equation. I used Mathematica and Fortran, I used Python to solve this differential equation. If I have, like in my case, the non-linearity is there in my differential equation. So I use a, like a platform called MatCont. MatCont. It's a very good. Still, it is there. It's called MatCont. It is short form for MATLAB continuation. It's a part of MATLAB. You can install this platform. You can use to study when it comes to materials. Okay. So how far this can help you to simulate the qubits is little bit questionable. If you have to study the qubits, you have to use the Hamiltonian formalism or density matrix formalism to define the qubit and its surrounding, and then use some programming like Qiskit or penny lane or strawberry fields and study that. Okay, so you have to pick depending on your problem. So probably you have to do a little bit more work on that to figure out which software. For me, if there is a non-linearity is there in the system, to study that, MatCont is a very good software. Okay, right. So what is a pi square by 2m? Rajesh Churasia, it should be p square by, yeah, like you were saying kinetic energy is p square by m. No, actually it is p square by 2m. Okay. Usually it is half mv square kinetic energy multiplied by m by m. M into v is a linear momentum. So what I'll get? P square by 2m. Okay. So I wrote P square by 2m. Yeah. If I missed two, you please, yeah, I consider that correction. Okay. Every quantum dot is a nanoparticle, but not all nanoparticles are quantum dots, sir. Is that their size only defines is in nanoparticles or quantum dots? So yeah, you are right in a way. The size means in a nano size, 1 nanometer size, let's say three-dimensional, there is a spherical surface, spherical area of one nanometer size radius. In that area, how many electrons I'm going to confine? Okay, so depending on the electron, the size is going to be defined. Accordingly, their excitation is going to be decided. So that means that particular color only they respond. That is how it is going to be uh, classified. Okay, right? So yeah, not all nanoparticles could be a quantum dot, because any nanoparticle means a particle of size nanometer. Okay, but quantum dots are a three-dimensional confinement in a nanoscale region of electric charges like electrons. So that's why it is going to exist in a superposition state of various charged possibilities, just like atom being existing various charges, various orbits, yeah, when it comes to its electron. Okay, how are quantum dots are excited? Just like any excitation you give with the electromagnetic wave, you can excite. Okay, we have a figure, right? We were showing, let's say you shine a white light onto a quantum dot. Depending on its size, it excites using that frequency and emit after de-excitation. You see different colors. So that is what the quantum dots are showing. Different color means they're exciting to only particular frequency. Okay, right? Using electromagnetic light, you can excite them. Conventional light. Can you state the art of quantum computer in India? Okay, as of in India, when it comes to research, people are working on MRI's nuclear magnetic resonance based quantum computing, like ISAR Pune, ISAR Mohali. And when it comes to transmons, like a superconducting qubits, the people who are working is stay up for Mumbai, Professor Vijay Raghavan, you can explore their field. When it comes to photonic, I'm only listing few. Excuse me, I am not telling everyone. When it comes to photonic based, you can just check CM Chandrasekhar from ISC. They have a quantum chips. They're working on it. They're trying to build a scaling up of that. Okay. There are in the ISC itself. There is a trapped ion qubits people are exploring. Okay, and there is neutral atom based qubits. I don't know much, but when it comes to NV center sensing qubits, or the group, the NQM hub, the Mumbai, headed by Professor Kasturi Saha and Isar Bhopal, together they are exploring quantum dots, sorry, NV center based quantum qubits. Okay, you can explore them. Okay, SP are leverage Fox states of light. Okay, you mean to do, I think. Quantization, I think SPE. I'm not getting what it means, but anyway, the Fock state of a light. Okay, you are talking about quantization of a light being coherent or a Fock state or yeah, a number state, right? I think you meant is right. When I want to study how light interacts with this qubits, I have to understand using quantization. That is where I treat the light as quantized field. Okay. Okay, then what is the next question? Good evening. Do you have two more? Okay, that is related to the arrangement. Not able to hear. Okay, there is a one more question. Is my observation correct? MRI is going to be a quantum spin transition magnetic resonance imaging. Works due to quantum nuclear spin and the principle of nuclear magnetic resonance. Quantum dots are not involved. Okay, yeah, NMRI is single nuclear magnetic resonance, single nuclei being responding to external magnetic field. When it comes to quantum dot, a bunch of electron responding to external magnetic field or external electric field or external light. Okay, QLED is quantized electron energy level transitions like quantum dots. When quantized electron energy levels, okay, they respond. Yeah, you are right. You are absolutely right, Ambikaji. Okay. Can you please throw some light on IBM, okay, Condor 1000 plus qubits? To what extent it can serve the real world problems, especially in next era? See, the moment you get the large number of qubits, obviously it is going to make a big deal. You know why? It is going to give me a lot of memory storage and also memory processing. Okay, in the NISQ era, what happens? At the most, few qubits may become noisy. So in that case, what should I do? Out of the 1000 qubits, I will only able to realize some error-free, something called logical qubits. Means out of 1000, probably if I realize even 100 or 200 logical qubits, look at how much data I can store, 2 to the power of 100. So big. Okay, so that is going to be a big jump. Okay, so whatever they are proposing, IBM is going to be a game changer. Okay, despite having noisy. Okay, to research on quantum materials for qubits to simulation using espresso, can I do it? I'm not aware about this espresso. Yeah, I think so. You can try. Chandrasekharji. Thank you very much, sir. In broad, what is the difference between quantum materials and nanomaterials? Okay, nanomaterials still quantum. Okay, when you study them, if you study them together, if their property is going to become a classical, means no more probabilistic. In that case, I can't read them as a quantum material which can be useful for my quantum technology. If anything which can show qubit nature or a probabilistic nature, it is a very good means for my quantum technology. So that's the main difference. Okay, and I think final question: superconducting quantum devices operate at millikelvin temperature for coherence. From a research perspective, how feasible it is to translate the sensitivity of superconducting quantum circuits into practical quantum sensors for environmental or biological measurements at room temperature? So that's what superconductivity itself needs a cryogenic, right? Okay, if there is anything which can work at room temperature, that will be a very good asset for us to do a sensing. That's what doing with the NV centers. The NV center doesn't need a cooling. If superconducting material can exist at room temperature, okay, sometime back somebody claimed, so I don't want to go into that kind of a fuss. If there is any superconducting at room temperature, then again it is going to be a big game changer. Okay, so yes, we can think in that direction. Okay, yeah, anyone trying Octave for serious alternative for MATLAB? Yes, I agree. Octave is for Linux based MATLAB. You can try. Okay, whatever you do with the MATLAB, you can try there. Octave is also more or less exactly equivalent. Okay, I did use during my master's program. I did not use later. I hope somebody who's using nowadays can comment on that. Okay, then. Thank you very much. Plenty of questions. Excuse me for taking 15 minutes extra. Okay, I tried my best to touch all the questions. Okay, like somebody was saying, Happy Pi Day. Yes, thank you. Happy Friday to all the participants and Manoj sir and every organizers here. Thank you very much. I'll be sharing this both the PPTs loaded with lot of material and text. Okay, so when it comes to superconducting part, I have not added any figures. You know why? We already had a initial presentation, role of quantum materials. I gave for 1 hour. So there I added figures. Okay, so see here, LCR circuit. Okay, it's Hamiltonian. How once you do a quantization, what happens? Okay, so you can there. Yeah, we also touched topological materials, photonic materials. Okay, today only superconducting and semiconducting both were there. So you can go through all three of my PPTs and get lot of insights about the quantum materials as such. Okay, so that's about from my end. That's all. Thank you very much. I think I have one session, I guess. I will meet you in the next session. Thank you very much. Have a nice weekend. And I express my gratitude to once again Manoj sir and their team, Pili sir, for such a wonderful opportunity. And I got very good questions. And I even think on that. There is one question which was not able to answer straight away. So I'll be thinking on that. Okay, that's simulations. Okay, so that's all, sir, from my
Thank
end.
you so much, sir. Our also we express our deepest gratitude towards you for agreeing to uh, these lectures. And I know your talks are always interesting, very simple, easy to understand. And yeah, participants also, I think they feel the same way. So thank you so much, sir, once again. And yes, we will have some more lectures from your side. Okay.
Yeah, I'm adding my PPT straight away. So for the quiz, there are 6 questions added for 3 questions on the superconductivity materials, 3 questions on the semiconductor. So we have definitely touched those questions, right? If you can think, you can answer those questions. Not an issue. Okay, right. Okay, then see you in my next session. Bye bye. I'll be
Bye,
adding,
sir.
sir,
Bye.
Manoj sir, I'll be immediately adding my both the PPTs to the canvas.
Yeah, that is good actually. Someone was trying to see if they are being uploaded or not. So, yes, the
Mhm.
PPTs are already uploaded and recordings will also be available. They are actually readily available just after the lecture. Just check the links. Thank you, sir. Thank you once again and see you in the next lecture.
Yes, sir. Bye.
Bye.